The moon has been staring at you your entire life, and it has never once shown you its other face. Not during a full moon, not during an eclipse, not in any photograph taken from Earth in the history of human civilization. Half of our nearest celestial neighbor, the object closest to us in all of space, has remained completely hidden from every human eye for the entire span of our species, until 1959, when a piece of Soviet machinery finally tore the veil away. And what it found was not a mirror image of the side we know. It was a different world entirely. A battered, cratered highland with almost none of the dark plains that paint the familiar face above us. A crust nearly twice as thick in places, hiding a basin so large it ranks among the biggest impact scars in the solar system. The far side of the moon is not simply the part we cannot see. It may be the key to understanding how the moon itself was born, why it looks the way it does, and what violent history is written into the silence on the other side of the sky. If you find this kind of journey into the hidden corners of our own cosmic backyard fascinating, take a moment to like and subscribe. It helps this channel grow more than you might think, and I am grateful for every one of you who sticks around for these deep dives. Now, let's go around to the other side. Chapter 1. The Myth of the Dark Side. Before we go anywhere, we need to clear up the single most common misunderstanding about the moon, one repeated so often in casual conversation, in song lyrics, in movie titles, that it has become a kind of accepted folklore. People call it the dark side of the moon. It is not dark. It receives exactly the same amount of sunlight as the side facing Earth. Over the course of a lunar day, which lasts about 29.5 Earth days, every part of the moon's surface experiences roughly 2 weeks of sunlight, followed by roughly 2 weeks of darkness. The far side is not bathed in eternal night any more than the near side is. The correct term, the one used by astronomers and planetary scientists, is the far side. It is far in the sense of orientation relative to Earth, not far in the sense of distance, and definitely not dark in the sense of illumination. The confusion is understandable. The phrase dark side carries a poetic weight that far side simply does not. It suggests mystery, the unknown, the unseen. And in a strange way, that poetic instinct is not entirely wrong, even if the science behind it is. Because while the far side receives just as much sunlight as the near side, it remains dark to us in a different sense. It is dark to human knowledge. It is dark to human eyes. It is the side of our closest neighbor that no person living on the surface of Earth has ever laid eyes on directly. Not once, not for a single second in the entire history of our species. That is the real meaning hiding inside the myth. Not an absence of light, but an absence of sight. The moon is tidally locked to Earth, meaning the same hemisphere always faces us, the result of a gravitational relationship that took billions of years to settle into its current rhythm. Early in the moon's history, after its violent formation, it likely rotated much faster relative to Earth. Over enormous stretches of time, Earth's gravity acted on the moon's slightly uneven mass distribution, gradually slowing its rotation until it matched its orbital period exactly. This is called synchronous rotation, and it is common throughout the solar system. Many moons around Jupiter and Saturn are tidally locked to their parent planets in the same way. Once the moon's rotation synchronized with its orbit, one face became permanently turned toward Earth and the other permanently turned away. From that point forward, every human who ever looked up at the night sky, every ancient astronomer charting its phases, every poet writing about its glow, every culture building calendars and myths around its cycles, saw only one face. The other face existed in our collective blind spot for the entirety of recorded history. This single fact, that we have only ever seen half of our nearest neighbor with the naked eye, deserves a moment of reflection before we move forward into geology and spacecraft and crater statistics. There is something almost unsettling about it. We think of the moon as familiar, as known, as a fixture so constant in human experience that it borders on mundane. We have walked on it. We have brought rocks back from it. We have mapped its visible face down to the smallest crater since the invention of the telescope. And yet, for the vast majority of human history, an entire hemisphere of this familiar object was as inaccessible to us as the surface of a planet orbiting another star. We did not know its shape. We did not know its features. We did not know whether it looked anything like the side we could see. This is the first lesson the far side teaches us before we even discuss a single scientific detail. Proximity does not guarantee visibility. The closest object in space to Earth, the one we have stared at since before we had language to describe it, kept half of itself secret simply because of the mechanics of orbital physics. If something this close, this constant, this central to human culture and mythology could hide half its identity from us indefinitely, it forces a humbling question about everything else we assume we understand simply because it is nearby and familiar. Chapter 2. The First Glimpse. The story of how humanity finally saw the far side begins not with NASA but with the Soviet Union in the early years of the space race, when both superpowers were racing to claim a series of firsts in the new frontier above the atmosphere. On October 4, 1959, the Soviet Union launched Luna 3, a spacecraft designed specifically to photograph the lunar far side and transmit those images back to Earth. This was an extraordinary technical challenge for the era. The spacecraft had to travel to the moon, orient itself precisely using a primitive system of photocells that detected sunlight to determine spacecraft attitude, photograph the far side using an onboard camera system, develop the film automatically inside the spacecraft using a miniaturized photographic processing unit, and then scan those developed images line by line using a television-style transmission system to send the data back across the growing distance to Earth. Every one of these steps represented a serious engineering problem in 1959, a time when computers filled entire rooms and reliable automated systems were still in their infancy. The camera system aboard Luna 3 used two lenses, one with a longer focal length for detail and one with a shorter focal length for context, capturing images on a roll of film. After exposure, the film was developed on board using a fixing and developing process adapted from photographic technology of the era, essentially a tiny automated darkroom flying through space. The processed images were then scanned and converted into a signal transmitted back to Soviet tracking stations on Earth. The technical achievement cannot be overstated. The spacecraft was operating at distances where radio signals took over a second to travel one way, with no possibility of real-time human intervention if something went wrong, using technology that by today's standards would be considered primitive even for a child's toy. And yet it worked. Luna 3 captured 29 photographs of the lunar far side, though due to transmission difficulties and signal degradation, only about 17 produced usable images. These images were grainy, low resolution, and difficult to interpret with precision. But they were enough. For the first time in human history, scientists on Earth saw the shape and major features of the hemisphere that had remained hidden since before humanity existed to look at it. The images revealed something immediately striking, something that would take decades of further exploration to fully explain. The far side looked different. Where the near side displayed large dark patches, the Luna Maria, vast plains of ancient volcanic basalt that paint the familiar face we see from Earth, the far side showed almost none of this. It was dominated instead by lighter-colored terrain, heavily cratered, more uniform in texture, lacking the dramatic dark and light contrast that gives the near side its recognizable pattern. Soviet scientists named several of the features they identified, including a large dark patch they called Mare Moscoviense, the Sea of Moscow, one of the very few Maria found on the far side, and a prominent crater they named in honor of Konstantin Tsiolkovsky, the pioneering rocket scientist whose equations underpin all of modern spaceflight. The political dimension of this achievement cannot be separated from the science. This was 1959, 2 years after Sputnik, in the heart of a space race driven as much by Cold War competition as by scientific curiosity. The Soviet Union's success in photographing the far side was trumpeted as a triumph of Soviet science and engineering, a demonstration that the same nation that launched the first satellite could also achieve feats of precision spacecraft control across hundreds of thousands of kilometers. For the United States, still recovering from the psychological shock of Sputnik, the Luna 3 images were a reminder that the Soviet space program was not a one-time fluke, but a sustained and capable effort. But beyond the geopolitics, something genuinely new had entered human knowledge. An entire hemisphere of our closest celestial neighbor, invisible to every human eye in history, had finally been seen, however imperfectly, however grainy and indistinct those first images may have been by modern standards. Chapter 3. Refining the Picture. Luna 3 was a beginning, not an ending. The images it produced, while historic, were far too low in resolution and too limited in coverage to provide a complete or detailed map of the far side. Filling in the picture would take more than a decade of continued effort from both the Soviet and American space programs. The Soviet Union continued its lunar exploration program with subsequent lunar missions, several of which provided additional imaging of both the near and far sides as spacecraft orbited the Moon on various trajectories. Zond 3, launched in 1965, captured additional photographs of the far side with improved camera technology, filling in gaps left by Luna 3 and providing higher resolution coverage of areas that had been poorly imaged in the original mission. On the American side, the lunar exploration effort took a different but complementary path. The Lunar Orbiter program, a series of 5 robotic missions launched between 1966 and 1967, was designed primarily to scout potential landing sites for the upcoming Apollo missions. But in the process, these spacecraft captured extensive photographic coverage of the Moon, including significant portions of the far side. Lunar Orbiter spacecraft used a sophisticated camera system that could photograph the surface, develop the film on board, and then scan the images for transmission back to Earth. Similar in principle to the Luna 3 system, but with substantially improved resolution and coverage. By the end of the Lunar Orbiter program, scientists had compiled photographic coverage of the vast majority of the lunar surface, both near and far sides, providing the detailed mapping data necessary for both scientific study and mission planning. The most direct human encounter with the far side came not through robotic cameras, but through human eyes during the Apollo missions of the late 1960s and early 1970s. As Apollo spacecraft carried astronauts on trajectories around the Moon, those astronauts became, briefly, the only human beings in history to personally witness the far side with their own eyes, rather than through photographs. The crew of Apollo 8, the first crewed mission to orbit the Moon in December 1968, became the first humans to see the far side directly, observing it during the portions of their orbital path when the Moon's bulk blocked all radio communication with Earth, the same blackout period that would become a recurring feature of every subsequent crewed lunar mission. Astronaut accounts from these missions describe the far side in terms that echoed the early photographic evidence. A landscape dominated by craters, lacking the dramatic dark plains familiar from Earth-based observation of the near side. A terrain that one astronaut famously described as looking like a battlefield, scarred and pockmarked across nearly its entire visible extent. These first-hand human observations, combined with continued robotic photography from both superpowers' space programs, gradually built up an increasingly detailed and accurate picture of what the far side actually looked like. By the time the Apollo program concluded in 1972, humanity possessed reasonably comprehensive photographic coverage of the lunar far side, though detailed scientific instrumentation, the kind needed to measure crustal thickness, gravitational variations, and surface composition with precision, would not arrive until decades later with a new generation of dedicated lunar orbiting spacecraft. Chapter 4. A Tale of Two Faces. Once scientists had sufficient data to compare the near and far sides in detail, a puzzle emerged that would occupy lunar science for decades and remains an active area of research even today. The two hemispheres of the Moon are strikingly different from each other, and explaining why has proven to be one of the more persistent challenges in planetary science. The most visually obvious difference lies in the distribution of the lunar Maria, the dark, relatively smooth plains formed by ancient volcanic activity that flooded large impact basins with basaltic lava billions of years ago. On the near side, the Maria cover roughly 31% of the surface, forming the recognizable dark patches that have inspired mythology and folklore across virtually every human culture that has gazed up at the Moon, from the man-in-the-moon imagery common in Western tradition to the rabbit-pounding rice cake imagery found across many East Asian cultures. These Maria are extensive, interconnected in places, and dominate the visual character of the near side as seen from Earth. On the far side, by stark contrast, the Maria cover only about 1 to 2% of the surface. The far side is overwhelmingly composed of lunar highlands, the lighter-colored, heavily cratered terrain that represents the Moon's ancient original crust, largely unmodified by the kind of extensive volcanic resurfacing that characterizes much of the near side. This is not a subtle difference. It is one of the most dramatic asymmetries found anywhere in the solar system between the two hemispheres of a single body. Why would one side of the Moon experience extensive volcanic flooding while the other side remained comparatively pristine highland terrain? Several hypotheses have been proposed over the decades, each addressing different pieces of the puzzle, and the current scientific understanding likely involves a combination of factors rather than a single simple explanation. One major factor involves the distribution of heat-producing radioactive elements within the lunar crust and mantle. Data gathered by orbiting spacecraft, particularly through gamma-ray spectroscopy, that can detect the signatures of radioactive decay, revealed that the near-side crust contains significantly higher concentrations of potassium, rare earth elements, and phosphorus, collectively referred to by the acronym KREEP, derived from the chemical symbols and abbreviation for these elements. These elements are associated with radioactive isotopes, including isotopes of uranium and thorium, that generate heat through radioactive decay over geological time. A near-side crust enriched in these heat-producing elements would have experienced more internal heating, potentially keeping the underlying mantle warmer and more prone to partial melting, generating the magma that eventually erupted to form the Maria. The far side crust, comparatively depleted in these elements, would have experienced less internal heating, reducing the volcanic activity that could have created equivalent Maria deposits. But this explanation raises its own question. Why would these heat-producing elements be unevenly distributed between the two hemispheres in the first place? This connects to a second major factor: the difference in crustal thickness between the near and far sides. Data from later lunar missions, including detailed gravitational mapping, revealed that the far side crust is, on average, substantially thicker than the near side crust, in some regions by tens of kilometers. A thicker crust would present a more significant barrier for magma rising from the mantle, making it harder for volcanic material to reach the surface and erupt, even in regions where mantle heating might otherwise be sufficient to generate magma. This crustal thickness difference itself demands an explanation, and this is where the story connects to the most violent chapter in the Moon's geological history, a single impact event so large that it may have reshaped half a world. Chapter 5. The South Pole-Aitken Basin. If you want to understand the single most important geological feature on the lunar far side, you need to understand the South Pole-Aitken Basin, an impact structure so enormous that it ranks among the largest confirmed impact basins anywhere in the solar system. The basin spans approximately 2,500 kilometers in diameter and reaches depths of up to 8.2 kilometers below the surrounding terrain, dwarfing virtually every other impact feature found on the Moon, Mars, or Mercury. To put that scale into perspective, the diameter of the South Pole-Aitken Basin is comparable to the distance across the entire continental United States, or roughly 2/3 the diameter of the Moon itself. This is not simply a large crater. It is a wound in the surface of an entire world, formed by an impact so violent that it remains one of the most studied and debated events in the history of the solar system. The basin formed early in lunar history, likely within the first several hundred million years after the Moon itself coalesced, during a period when the inner solar system was still being bombarded by large planetesimals left over from planet formation. The impactor responsible for creating the South Pole-Aitken Basin must have been enormous, likely tens of kilometers across, striking the Moon at velocities of many kilometers per second, releasing energy that by some estimates exceeded the combined output of every nuclear weapon ever created, multiplied by factors that strain ordinary comprehension. An impact of this magnitude does not simply excavate a crater. It fundamentally alters the geological structure of the surrounding region across enormous distances. The energy released would have melted and ejected enormous quantities of crustal and mantle material, potentially excavating all the way through the original crust and into the underlying mantle in the basin's deepest regions. This is significant because it directly connects to the crustal thickness asymmetry discussed in the previous chapter. Some scientific models propose that the South Pole-Aitken impact event was responsible, at least in part, for redistributing crustal material across the Moon, potentially thinning the crust in the immediate impact region, while thickening it in other areas through the ejection and redeposit of material, or through subsequent geological processes triggered by the impact's aftermath. Other models suggest the impact may have influenced the distribution of heat-producing elements, potentially excavating material from depth and redistributing it in ways that affected subsequent volcanic activity across the far side. The basin itself is located primarily on the far side, centered near the lunar South Pole, and its presence dominates the geological character of an enormous fraction of the far side hemisphere. Some of the deepest, most ancient exposed material on the Moon can be found within this basin, material that may provide a direct window into the Moon's earliest crust and even into material from its mantle, material that would otherwise remain buried under kilometers of subsequent geological deposits anywhere else on the lunar surface. This is precisely why the South Pole-Aitken Basin has become one of the most scientifically prized targets for future lunar exploration. A mission that could land within this basin and return samples would potentially be sampling material unlike anything brought back during the Apollo program. Material that could answer fundamental questions about the Moon's internal structure, its early differentiation into crust, mantle, and core, and the violent bombardment history of the early solar system. The basin's age itself remains a subject of active research and debate. Some estimates place its formation at over 4.3 billion years ago, making it among the oldest preserved large-scale geological features anywhere in the solar system. A frozen snapshot of conditions in the solar system's earliest, most chaotic chapter, preserved because the Moon, unlike Earth, lacks plate tectonics, weather erosion, and an active hydrosphere that would have erased such ancient scars over geological time. Earth almost certainly experienced impacts of comparable or even greater magnitude during the same early period of solar system history. But Earth's active geology, its tectonic plates constantly recycling crust, its atmosphere and oceans driving erosion, and billions of years of subsequent geological activity have erased virtually all direct physical evidence of these ancient impacts from the terrestrial surface. The Moon, geologically inert for billions of years, preserves this violent history in plain sight, written across the far side in the form of the South Pole-Aitken Basin and the countless craters surrounding it. Chapter 6. A heavily cratered memory. Beyond the South Pole-Aitken Basin itself, the far side as a whole is distinguished by an extraordinarily high density of impact craters compared to the near side, a difference that itself requires explanation and connects to broader questions about the Moon's history and its relationship with Earth. The near side Maria, those vast volcanic plains, are relatively young in geological terms, having formed through volcanic flooding that buried older, more heavily cratered terrain beneath fresh basaltic rock. This volcanic resurfacing effectively erased much of the older cratering record on significant portions of the near side, replacing ancient battered terrain with comparatively smooth, younger volcanic plains that have since accumulated a more modest density of impact craters from subsequent, less intense bombardment in more recent geological history. The far side, having experienced far less volcanic resurfacing, retains its ancient highland terrain largely intact, preserving billions of years of accumulated impact craters without the burial and erasure that affected so much of the near side. This means that when scientists look at the far side, they are looking at a far more complete and ancient record of the Moon's bombardment history, a surface that has recorded impacts across a much longer span of time without the periodic resetting that volcanic flooding provided on parts of the near side. This cratering record is not merely an aesthetic curiosity. It serves as a crucial scientific tool because the Moon's heavily cratered, geologically stable surface functions as something like a fossil record for the entire inner solar system. By studying the size, distribution, and relative ages of craters on the lunar far side, scientists can reconstruct the history of impact bombardment throughout the inner solar system over billions of years, information that is largely inaccessible on Earth due to our planet's active geology erasing the evidence. This connects to one of the most important concepts in planetary science, the lunar cratering chronology, a system developed using radiometric dating of Apollo and lunar sample materials combined with crater counting statistics, which allows scientists to estimate the age of various lunar surfaces based on how many craters of various sizes have accumulated on them. This chronology, calibrated using actual lunar samples whose ages were measured directly through radioactive decay dating in laboratories on Earth, has become a fundamental tool for estimating the ages of surfaces, not just on the Moon, but on Mars, Mercury, and other bodies throughout the solar system, places where we do not yet have physical samples to date directly. In this sense, the far side of the Moon, simply by virtue of having preserved its ancient cratered terrain so thoroughly, has become an indispensable scientific reference for understanding the chronological history of the entire inner solar system. Every estimate of when a particular region of Mars formed, when certain features on Mercury were created, depends in some way on calibration data ultimately derived from careful study of lunar surfaces, including extensively from the far side's well-preserved highland terrain. The relative absence of large-scale resurfacing on the far side has, in an almost ironic twist, transformed the side of the Moon we could not see for most of human history into one of the most scientifically valuable surfaces in the entire solar system for understanding deep time. Chapter 7. Listening from the quiet side. Beyond geology, the far side of the Moon possesses a property that has captured the attention of an entirely different scientific community, radio astronomers and physicists studying the deepest reaches of the universe. The far side, by virtue of its permanent orientation away from Earth, is permanently shielded from the enormous volume of radio frequency noise generated by human civilization on Earth. Every television broadcast, every radio station, every cell phone signal, every radar system, every piece of electronic equipment on the surface of our planet contributes to a constant background hum of electromagnetic interference that blankets near-Earth space and makes certain types of extremely sensitive radio astronomy observations difficult or impossible to conduct from Earth's surface or even from orbit around Earth. The Moon itself, with its substantial bulk, blocks this terrestrial radio noise from reaching its far side, creating what radio astronomers refer to as the quietest radio environment available anywhere in the inner solar system, a natural shield blocking out the electromagnetic chatter of an entire civilization. This matters enormously for certain types of astronomical observation, particularly the study of extremely faint, extremely low-frequency radio signals from the distant universe, including signals associated with the cosmic dark ages, the period in the early universe before the first stars formed, when the universe was filled with neutral hydrogen gas that emits and absorbs radiation at a specific low frequency known as the 21-centimeter line. Detecting these signals requires instruments shielded from terrestrial interference at a level that is exceptionally difficult to achieve anywhere on or near Earth. The far side of the Moon, naturally shielded by over 3,000 kilometers of solid rock from the entire radio noise output of human civilization, represents one of the most promising potential locations for building radio telescopes capable of conducting this kind of extraordinarily sensitive research. Multiple space agencies and research institutions have proposed concepts for far-side radio observatories over the years, ranging from arrays of relatively simple antenna systems that could be deployed by robotic landers to far more ambitious concepts involving large-scale radio telescope arrays constructed using lunar regolith and local resources, taking advantage of the far side's natural radio silence to conduct observations that would be effectively impossible from anywhere on or near Earth. China's Chang'e 4 mission, which became the first spacecraft to successfully achieve a soft landing on the lunar far side in January 2019, carried with it a low-frequency radio astronomy experiment specifically designed to take advantage of this unique quiet environment, representing one of the first practical scientific efforts to capitalize on the far side's radio silence. The implications extend beyond pure astrophysics. A sufficiently sensitive radio observatory on the far side could, in principle, also serve as an extraordinarily capable tool for searching for technosignatures, the hypothetical radio emissions that might be produced by extraterrestrial, technological civilizations elsewhere in the galaxy, signals that would otherwise be exceptionally difficult to distinguish from the noise generated by our own planet's saturated radio environment. The far side, in other words, is not merely a geological curiosity or a historical footnote about hidden landscapes. It may become, in the coming decades, one of the most important locations in the solar system for humanity's effort to listen to the deepest, quietest whispers of the cosmos, a role made possible specifically because it sits in permanent radio shadow from the noise of our own civilization. Chapter 8. The Communication Problem. The same orientation that makes the far side valuable for radio astronomy creates one of the most persistent practical challenges for any mission attempting to operate there. Because the far side never faces Earth, any spacecraft, rover, or human mission operating on that hemisphere cannot communicate directly with Earth using simple line-of-sight radio transmission. The bulk of the Moon itself sits directly between the far side surface and our planet, blocking any direct signal path. This is not a minor inconvenience. It is a fundamental engineering obstacle that any far side mission must solve before it can function at all. During the Apollo missions, this communication blackout was experienced directly by every crew that orbited the Moon. As the spacecraft passed behind the Moon during each orbit, radio contact with Mission Control in Houston was completely severed for the duration of the time the spacecraft remained on the far side, typically lasting around 45 minutes per orbit depending on the specific trajectory. During these blackout periods, astronauts were entirely on their own, with no possibility of real-time guidance, troubleshooting assistance, or even simple reassurance from ground control. Apollo 8 Commander Frank Borman and his crew became the first humans in history to experience this isolation, watching the Earth disappear behind the lunar horizon and losing all radio contact with their home planet, even as they remained close enough to see the far side terrain passing beneath their spacecraft window. For a single orbiting spacecraft, this blackout period was manageable, a known and temporary gap in communication that the mission could plan around. But for any sustained operation on the far side surface itself, Whether a robotic lander, a rover, or eventually a permanent human installation, a temporary communication blackout is not an option. Continuous communication with Earth is essential for transmitting scientific data, receiving operational commands, and maintaining the kind of real-time oversight that complex missions require. The solution that has emerged, and the one currently in active use by lunar missions targeting the far side, involves deploying a relay satellite into a specific orbital position that maintains line-of-sight visibility to both the far side surface and Earth simultaneously. China's Chang'e 4 mission, the first to successfully land on the far side, relied on a dedicated relay satellite named Qiao, meaning Magpie Bridge, a reference to a Chinese folk tale in which magpies form a bridge across the sky to reunite separated lovers. Qiao was positioned in a specialized orbital location known as a halo orbit around the second Earth-Moon Lagrange point, a gravitationally stable position located beyond the Moon as seen from Earth, where the combined gravitational influences of Earth and the Moon allow a spacecraft to maintain a relatively stable position using minimal fuel for station keeping. From this vantage point, Qiao maintains a continuous line of sight to both the far side lander and to Earth, allowing it to function as a communication relay, receiving signals from the surface mission and retransmitting them toward Earth, and vice versa for commands sent from ground control. This solution, while effective, adds an entire additional layer of mission complexity and risk. Before any spacecraft can successfully land on and operate from the far side, an entirely separate relay satellite must first be successfully launched, positioned with precision in its specialized orbit, and verified to be functioning correctly, all before the actual surface mission can even attempt its landing. Any failure in the relay satellite renders the surface mission effectively blind and mute, unable to communicate with Earth regardless of how successfully it otherwise performs. This requirement for relay infrastructure represents one of the clearest practical illustrations of how the far side's greatest scientific assets, its isolation from terrestrial radio noise, and its hidden geological history, are inseparably linked to its greatest operational challenges. The very feature that makes the far side valuable for radio astronomy, its permanent orientation away from Earth, is the same feature that makes direct communication with any far side mission impossible without additional relay infrastructure. There is no version of far side exploration that avoids this trade-off. Every mission must either accept the communication blackout as the Apollo astronauts did, treating it as a temporary, predictable gap, or invest in the additional complexity, cost, and risk of relay satellite infrastructure to maintain continuous contact, as Chang'e 4 successfully demonstrated, and as future missions, including those planning to establish more permanent far side installations, will need to replicate or improve upon. Chapter 9. Touching down on the other side. For decades after Luna 3 first photographed the far side and Apollo astronauts personally observed it from orbit, the far side surface itself remained completely untouched by any spacecraft. Every successful soft landing on the Moon, from the Soviet lunar program through the American Apollo missions through the various robotic missions of subsequent decades, had targeted the near side, both because near side landing sites allowed for direct radio communication with Earth without relay infrastructure, and because the near side had been more extensively studied and mapped, making mission planning and landing site selection comparatively straightforward. This changed on January 3, 2019, when China's Chang'e 4 mission successfully achieved the first soft landing on the lunar far side in the history of space exploration. a genuine milestone that required solving the communication relay problem described in the previous chapter as a prerequisite. The mission targeted von Karman crater, a large impact crater located within the South Pole-Aitken basin, chosen specifically because of the basin's extraordinary scientific significance as one of the oldest and deepest exposed geological features anywhere on the Moon. The Chang'e 4 mission consisted of a stationary lander and a small rover named Yutu-2, meaning Jade Rabbit, a reference to the rabbit companion of the moon goddess Chang'e in Chinese mythology. Yutu-2 became the first wheeled vehicle in history to traverse the lunar far side surface, conducting a sustained program of geological investigation that has continued for years beyond its originally planned mission duration, vastly exceeding expectations for operational longevity in the harsh lunar environment. The scientific instrumentation carried by Chang'e 4 and Yutu-2 included cameras for surface imaging, a ground-penetrating radar system capable of probing subsurface geological structure, spectrometers for analyzing surface mineral composition, and the low-frequency radio astronomy experiment mentioned in the previous chapter, designed to take advantage of the far side's unique radio-quiet environment. Among the most scientifically significant findings from the mission has been evidence regarding the subsurface composition within von Karman crater, including measurements suggesting the presence of material that may have originated from deep within the lunar mantle, potentially excavated and exposed by the South Pole-Aitken impact event billions of years ago. If confirmed and further characterized through additional research, this would represent direct physical evidence of mantle material accessible at or near the surface, material that elsewhere on the Moon would remain buried under many kilometers of overlying crust, providing scientists with an unprecedented opportunity to study the composition of the lunar interior without the need for deep drilling or sample return missions that could directly access true mantle material. Chang'e 4's success opened the door for continued far-side exploration, and China's lunar program has continued building on this foundation. Chang'e 6, launched in 2024, achieved another historic first by successfully collecting samples from the lunar far side and returning them to Earth, the first time in history that physical material from the far side has been brought back for detailed laboratory analysis, using instrumentation far more sophisticated and precise than anything that can be miniaturized and sent to the Moon aboard a robotic lander. The samples returned by Chang'e 6 were collected from within the South Pole-Aitken basin, specifically targeting material that scientists hope will help resolve long-standing questions about the basin's formation, its age, and its role in shaping the broader crustal asymmetry between the Moon's two hemispheres. Early analysis of these returned samples has already provided new constraints on the age of the South Pole-Aitken basin and on the volcanic history of the far side, representing the first ground truth data, actual physical material analyzed in terrestrial laboratories, available for a region of the Moon that for 60 years existed only as a subject of remote photography and orbital instrument measurements. This progression from grainy 1959 photographs to laboratory analysis of physical samples in the 2020s represents one of the more remarkable trajectories in the history of planetary exploration. A hemisphere that began as nothing more than a blurry outline, gradually transforming into a target of detailed, sample-based scientific investigation. Chapter 10. Why the far side matters for the future. The scientific value of the far side extends well beyond satisfying historical curiosity about what lies on the other side of our nearest celestial neighbor. As space agencies around the world look toward more ambitious lunar exploration programs, including plans for sustained human presence on the Moon, the far side has emerged as a location of particular strategic and scientific interest for several converging reasons. The radio-quiet environment discussed earlier represents perhaps the most unique resource the far side offers, a natural laboratory condition that cannot be replicated anywhere else in the inner solar system without traveling to genuinely remote locations far more difficult to reach and operate from than the Moon. As radio astronomy continues pushing toward ever more sensitive observations of the early universe, the demand for genuinely radio-quiet observation sites will likely only increase, and the far side remains the most accessible location offering this property. The South Pole-Aitken basin and its surrounding terrain represent a second major draw, offering scientists access to some of the oldest, most pristine geological material anywhere on the Moon. Material that could answer fundamental questions not just about lunar history, but about the broader history of the early solar system and the bombardment environment that shaped the inner planets during their formative first several 100 million years. Every sample returned from this region adds to our understanding of an era in solar system history that remains frustratingly difficult to study directly anywhere else, since Earth's active geology has erased virtually all comparable evidence from our own planet's earliest history. There is also growing interest in the lunar South Pole region specifically, which sits near the South Pole-Aitken basin and has been identified through orbital remote sensing as potentially harboring significant deposits of water ice within permanently shadowed crater floors that never receive direct sunlight due to the extreme low-angle illumination near the lunar poles. While this water ice potential applies to the South Polar region broadly, rather than being exclusively a far-side phenomenon, the geographic overlap between scientifically valuable far-side terrain and potentially resource-rich polar regions has elevated the broader South Polar and far-side area as a priority target for numerous national space agencies and private exploration initiatives looking toward the future of sustained lunar activity. NASA's Artemis program, designed to return American astronauts to the lunar surface for the first time since the Apollo era, has identified the lunar South Pole region as a primary target for crewed landings, citing both the scientific interest in potential water ice deposits and the broader strategic value of establishing a sustained human presence in a region offering unique resources and scientific opportunities unavailable at lower latitudes. While Artemis landing sites under current planning are generally located on terrain visible from or near the boundary with the near side rather than deep within the far side proper, the broader scientific rationale driving interest in this region, water ice resources, ancient preserved geology, and proximity to the South Pole-Aitken basin's scientific treasures draws directly from the decades of far-side research and exploration that began with Luna 3 in 1959 and has continued through Chang'e 4 and Chang'e 6 in more recent years. Beyond any single nation's program, there is a broader strategic dimension to far-side exploration that deserves acknowledgement. The far side's radio-quiet environment, were it to be developed for sustained astronomical use, would represent an extraordinarily valuable scientific resource, one that multiple nations and research institutions have expressed interest in preserving and potentially formalizing protections around, similar in spirit to how certain remote locations on Earth, including parts of Antarctica and specific radio-quiet zones established around major terrestrial radio observatories, have been designated for scientific protection from interference. As more nations and private companies develop the capability to land spacecraft on the far side, questions about how to balance scientific preservation of this unique radio environment against other potential uses, including future communication infrastructure or resource extraction activities, will likely become an increasingly important topic in discussions of lunar governance and the broader framework of space law that governs activity beyond Earth. Chapter 11. What the hidden side teaches us. Step back now from the specific details of craters, basins, radio telescopes, and robotic rovers, and consider what the far side of the Moon represents at a broader level, both scientifically and as a kind of metaphor worth carrying with us. For the entire span of human history before 1959, an enormous and significant portion of our nearest neighbor in space, an object visible every single night, central to mythology, religion, timekeeping, and culture across every human civilization that has ever existed, remained completely unknown to us. Not because it was difficult to reach in any physical sense. The far side is, after all, no farther from Earth in terms of average distance than the near side, separated by the same roughly 384,000 kilometers that define the Earth-Moon distance overall. It remained unknown purely because of orbital geometry, the simple, mechanical fact of tidal locking that kept one face perpetually turned away from every human eye that ever looked skyward. This is worth sitting with for a moment. We often assume that what is close to us is, by virtue of that closeness, known to us. We assume that proximity implies familiarity, that nearness implies understanding. The far side of the Moon stands as one of the clearest demonstrations in the entire natural world that this assumption can be false. Something can sit at the absolute closest possible distance from Earth, can be the single most prominent object in our night sky after the Sun, can have been observed and studied by human beings for the entirety of recorded history, and can still keep half its true nature hidden, not through any deliberate concealment, but simply through the quiet mechanics of gravity and rotation operating over geological time. When Luna 3 finally captured those first grainy images in 1959, what scientists discovered was not simply new data. They discovered that their existing assumptions, built entirely on observations of the visible near side, had led them toward an incomplete and in some ways misleading picture of what the Moon actually was. The assumption that the far side would mirror the near side, that it would show similar proportions of dark maria and light highland terrain, similar crater densities, similar overall character, turned out to be wrong in ways that opened up entirely new scientific questions rather than confirming existing expectations. This is perhaps the deepest lesson embedded in the story of lunar far side exploration. Sometimes the most important discoveries do not confirm what we already believe. They reveal that our existing picture, built from whatever limited vantage point we have access to, was never the complete picture to begin with. The near side of the Moon, for all of recorded human history, was treated as essentially equivalent to the Moon itself, simply because it was the only side anyone could see. Mythology built around lunar markings, scientific theories about lunar formation, artistic and cultural representations across every civilization on Earth, all of it was built on data from exactly one hemisphere, with the implicit and entirely unconscious assumption that this hemisphere told the whole story. It did not. The far side's dramatically different geological character, its thicker crust, its scarcity of volcanic plains, its ancient and well-preserved cratering record, all of this forced a fundamental revision of scientific understanding, about how the moon formed, how it evolved, and why its two hemispheres diverged so dramatically from one another over billions of years of geological history. There is a practical principle embedded here that extends well beyond lunar science. Whenever we form a complete picture of something based on partial access, whether that something is a celestial body, a historical event, a person, or a complex system of any kind, we should hold that picture with appropriate humility, recognizing that our vantage point, however constant and familiar it may feel, may simply be the only side we have ever had access to see. The moon taught us this lesson directly and concretely, but the underlying principle that visibility is not the same as completeness, that the familiar face is not necessarily the whole story, applies far beyond astronomy. Chapter 12. The quiet permanence of the other side. There is something almost meditative about the lunar far side that deserves acknowledgement before we close this exploration, something that goes beyond pure scientific data and touches on a more contemplative dimension of what this hidden hemisphere represents. The far side has existed in its current orientation, permanently turned away from Earth for an enormous span of geological time, likely for at least the past several 100 million years, if not considerably longer, as the moon's rotation gradually synchronized with its orbital period following its formation. Throughout this entire span, regardless of every human civilization that has risen and fallen on Earth, regardless of every war, every empire, every scientific revolution, every cultural transformation that has reshaped human society across recorded history and the unrecorded millennia before it, the far side simply continued facing away, accumulating its slow record of micrometeorite impacts, cosmic ray exposure, and the occasional larger collision event indifferent to anything happening on the planet it orbits. There is a particular kind of patience embedded in geological timescales that human minds, accustomed to operating on scales of days, years, and at most a few generations, struggle to genuinely internalize. The South Pole-Aitken basin, that enormous scar covering a significant fraction of the far side, formed over 4.3 billion years ago, a span of time so vast that it predates not just human civilization but multicellular life itself, predates the emergence of complex life of any kind on Earth, predates even the earliest evidence of single-celled microbial life in the geological record. The basin has simply sat there, slowly accumulating additional smaller impacts on top of its original structure for the entire subsequent history of life on Earth, through every evolutionary transition, every mass extinction, every geological epoch that textbooks divide Earth's history into. When Chang'e 4 touched down within von Karman crater in January 2019, it was landing on terrain that had remained essentially undisturbed by anything beyond micrometeorite impacts and cosmic ray exposure for billions of years, a level of geological stillness that has no real equivalent anywhere on Earth's constantly shifting, eroding, tectonically active surface. This permanence offers a different kind of perspective on the far side beyond pure scientific utility. It is not merely a useful location for radio telescopes or a scientifically interesting target for sample collection. It is one of the most stable, unchanging physical records available anywhere in our cosmic neighborhood, a place where the deep past of the solar system remains essentially frozen in place, waiting for sufficiently capable instruments and curious minds to read what it has preserved. For 60 years, human beings have been gradually learning to read that record, starting with grainy photographs that revealed nothing more than rough outlines and shadows, progressing through detailed orbital mapping that revealed crustal thickness variations and elemental composition, advancing further still through an actual robotic landing that placed instruments directly on the ancient surface, and culminating, for now, in physical samples returned to laboratories on Earth, where scientists can examine lunar material with the full power of modern analytical chemistry and isotope dating techniques. Each step in this progression has added detail and nuance to our understanding, but the fundamental story has remained consistent since those first 1959 images. The far side is not simply the back of a familiar object. It is a genuinely different landscape, shaped by different processes, preserving a different and in some ways more complete record of the Moon's earliest and most violent history, hidden from human sight for the entire span of our species' existence, not because anyone intended to hide it, but simply because the universe arranged its orbital mechanics in a way that happened to keep this particular face turned away from the one vantage point capable of appreciating what it held. Chapter 13. Looking Forward. As this exploration of the lunar far side draws toward its conclusion, it is worth considering where this story goes next, because unlike many chapters of scientific discovery that reach a kind of natural resolution, the investigation of the far side remains very much an active and ongoing pursuit. China has announced plans for continued lunar exploration, including additional sample return missions and eventually crewed lunar landing ambitions that would represent that nation's first human presence on the Moon's surface, with mission planning documents suggesting interest in eventually extending human exploration capability toward far-side targets as the broader program matures. International cooperation and competition in lunar exploration has intensified considerably in recent years, with multiple nations and private companies developing landing capabilities, and proposals for dedicated far-side radio astronomy missions continuing to circulate within the scientific community, seeking the funding and political support necessary to finally establish a permanent or semi-permanent radio observatory, taking full advantage of the unique quiet environment that no other accessible location in the solar system can offer. The broader vision shared by many planetary scientists involves eventually establishing far-side observation capabilities sophisticated enough to conduct genuinely groundbreaking astrophysical research, potentially including the detection of radio signals from the earliest periods of cosmic history. Signals so faint and at such specific low frequencies that no Earth-based or even near-Earth orbital instrument could realistically detect them, given the persistent radio noise generated by human civilization. There is also continued scientific interest in further sample return missions, targeting different regions of the South Pole-Aitken basin and other far-side locations, each additional sample providing further constraints on the basin's formation history, the broader bombardment chronology of the early solar system, and the underlying causes of the crustal and volcanic asymmetry between the Moon's two hemispheres that began this entire investigation. Some research proposals have even suggested that sufficiently detailed study of far-side materials, particularly any material that may have originated from deep within the lunar mantle as a result of the South Pole-Aitken impact excavation, could provide insights relevant not just to the Moon itself, but to broader questions about how rocky planets and large moons differentiate into core, mantle, and crust during their early formation. Insights that could inform our understanding of similar processes that occurred on Earth, Mars, and other rocky bodies throughout the solar system. Processes that in most cases have been obscured by billions of years of subsequent geological activity everywhere except on geologically quiet bodies like the Moon. 65 years after Luna. 3 first tore away the veil hiding half our nearest neighbor. The far side has progressed from an unknown blur to one of the most actively studied and strategically significant regions in all of lunar science, a transformation that captures something essential about the nature of scientific progress itself. We do not always know in advance which hidden corners will prove scientifically vital once finally revealed. The Soviet engineers who built Luna 3 in 1959 could not have anticipated that their grainy photographs would eventually lead towards serious proposals for cosmic dark ages radio astronomy, towards sample return missions targeting one of the largest impact basins in the solar system, or toward detailed scientific debates about crustal thickness and heat-producing element distribution that continue informing our understanding of how rocky worlds form and evolve. They simply wanted to see what was there, driven by curiosity and national ambition in roughly equal measure. What they found, and what subsequent decades of increasingly sophisticated exploration have continued to reveal, turned out to matter far more than anyone could have predicted from those first uncertain images. The far side of the Moon is not dark. It never has been. It receives the same sunlight, experiences the same roughly month-long cycle of day and night as the hemisphere we have always been able to see. But for the entire span of human existence before 1959, it remained completely hidden from us. Nonetheless, not through any darkness of illumination, but through the quiet, patient mechanics of tidal locking that kept one face of our nearest neighbor permanently turned away from every eye that ever looked up from the surface of Earth. What we found when we finally looked was not simply more of the same. It was a genuinely different world, sharing the same orbit as the one we thought we already knew. A hemisphere with a thicker crust, a battered and ancient highland surface nearly devoid of the dark volcanic plains that define its companion side, and, at its heart, a scar over 2,500 kilometers across, etched by an impact so violent that its true age stretches back to within the first few 100 million years of the solar system's existence. The far side has become a quiet laboratory for listening to whispers from the dawn of the universe, a target for sample return missions seeking to understand the earliest violence of planetary formation, and a permanent reminder that even the most familiar object in our sky, the one we have watched rise and set since before we had words to describe it, was never fully known to us at all. Half of it was always there, waiting in patient silence on the other side for the moment we finally found a way to look. If this journey into the hidden hemisphere of our closest neighbor expanded how you think about the Moon, consider subscribing for more deep dives into the corners of our solar system that most people never stop to consider. Thank you for watching all the way to the end. I'll see you in the next one.